Hello and welcome to this clip on shapes of molecules and ions. We'll start off by looking at how dot cross diagrams can actually be used to determine the lone pairs and bonding pairs of electrons within a covalent species. I say species because I'm talking about a molecule or an ion. Then we can move on to the simple molecular shapes that you need to know and how we work them out using an idea called valence shell electron pair theory. We'll look at one or two common trickier examples and how to work their shapes out, and then go through a range of worked exam question sections to show you how it can actually come out in a test. So for this to work, it's assumed that you're already comfortable with dot cross diagrams and covalent species. So starting off with electron pairs in dot cross diagrams, obviously the electron pairs that are in the overlaps between the shells, these are called bonding pairs, are indicated by the red arrows in the diagram. If you've got an electron pair that's not inside a shell overlap in a dot cross diagram, this is called a lone pair, and they're not involved in bonding. And I've now highlighted the lone pairs in blue, and I've also added a little bit to the information at the bottom, and it's just to say that bonding pairs are attracted to nuclei in both bonded atoms. If you go and look at your definition of covalent bonding, you'll see what I mean. And a lone pair is only attracted to one atom's nucleus, the atom that it's part of. So bonding pairs are attracted to two nuclei because of the nature of the covalent bond, and lone pairs are only attracted to one nucleus, so they're not involved in bonding. So valence shell electron pair theory has four important parts to it. First of all, electron pairs repel each other within a covalent molecule or species because they're both negative. So each pair is negatively charged, so they repel each other. Lone pairs repel more than bonding pairs because they're only held in place by the nuclear attraction of one nucleus, not two, as in bond pairs. So again, do have a look at the covalent bonding definition. The number of bonding pairs present in a molecular structure as opposed to the number of lone pairs can be used to determine the molecular shape. So we often look at the number of bond pairs and the number of lone pairs before deciding what shape to assign to that structure. And finally, the molecular shape adopted by molecule will be the one that has the least amount of repulsion between neighbouring electron pairs. So therefore the electron pairs will tend to arrange themselves geometrically around the central atom to allow this to happen. So we sometimes refer to electron pairs as regions of electron density. They can be a bonding pair, or they can be a lone pair. So just for illustrative purposes, you wouldn't have to do this if you were drawing the bonds as solid lines. I've added the bonding pairs, so you can see that they're regions of electron density. So using the key at the top left of the page, if you look across all the molecules that are in the screen, you'll see that you have some bonding pairs, and in purple you have some lone pairs on the fluorine. So looking at the molecule on the right hand side, boron trifluoride, it's taken to have three regions of electron density around the central atom. We don't take account of the other lone pairs that are on the periphery. If there happen to be lone pairs on the central atom somehow, then we'd be having a look at what their effect would be on the shape. So it's considered to have three regions of electron density. In this particular case and on this particular screen, the regions of electron density all happen to be bonding pairs. Before we get into drawing the three-dimensional shapes of molecules, we have to be able to draw molecules in three dimensions. And this is where we draw the bonds using different notations. A straight solid line, like you may have come across at GCSE, is just a line with no dashes in it. A wedge means the bond is coming out of the screen towards you, or out of the page towards you if you're looking at it on paper. And a dotted or dashed line, slowly getting more and more broad, means the bond is going into the screen away from you. And to illustrate this, I've applied it to the three types of bonds, not the three types of bonds, the three orientations of bonds in the three-dimensional shape of methane in the bottom right-hand corner. So the bond coming out is the wedge, the bond going in is the dashed line, and the solid lines are the bonds in the same plane as the screen. So we've mentioned regions of electron density already. What we need to look at now is what effect they'll have on the bond angles in the molecule. So if we assume that this screen deals with molecules with bonding pairs only around the central atom, or examples of those molecules, I'll take you through the three examples. So in each case, the central atom has been highlighted in purple. And I've now highlighted in a darker shade of blue the regions of electron density around each central atom. So you can see that one molecule has 4, one molecule has 2, and one molecule has 3. Now the number of regions of electron density means that the electron pairs around the central atom will orientate themselves in slightly different bond angles. And what they're trying to achieve is what's at the top of the screen. They're trying to get as far away as possible from each other. If you have 4 regions of electron density, that happens to give you a bond angle of 109.5 degrees. If they happen to have 3 regions of electron density, that gives you a bond angle of 120. If they have 2 regions of electron density, and make a note here that we consider double and triple bonds to be 1 region of electron density apiece, so therefore it's not 4 regions of electron density because you have 2 double bonds, it's 2 regions of electron density when you have 2 double bonds. In this case, the shape of least repulsion gives you a bond angle of 180 degrees. If we now start to mix it up a little bit and have in amongst our regions of electron density a mixture of bonding and lone pairs, what we need to remember is the lone pair bond pair repulsion is stronger than bond pair repulsion. And like we said earlier, lone pairs repel more than bonding pairs. So what happens is we keep in mind that there are 4 regions of electron density in these 3 examples. Some of those regions of electron density are bonding pairs. Some of those regions of electron density are lone pairs. So what happens if you have a lone pair instead of a bonding pair? What happens is the bond angle will decrease by 2.5 degrees. You can see this going from CH4 to NH3, and again from NH3 to H2O. At the bottom of the screen, I've put in the dot cross diagrams so you can use them to compare. So 4 bonding pairs of electrons in methane, as I've highlighted. There's 3 bonding pairs and 1 lone pair in ammonia, as I've also highlighted. And finally in water, 2 bonding pairs and 2 lone pairs. So next up, it's the shapes you have to remember. When this particular screen is finished, it's worth pausing the clip and doing a summary sheet of all of these different arrangements, because you need to be able to remember them in order to apply them to what you see in front of you when you get given an unfamiliar example in an exam. So for 2 regions of electron density, like we've said, the bond angle is 180 degrees. Not surprisingly, it's called linear. And 2 good examples to remember are beryllium chloride and carbon dioxide. So the next one is called trigonal planar, 120 degrees, 3 bonding pairs, no lone pairs, and an example would be boron trifluoride. The next one involves 4 bonding pairs, and it's 109.5 degrees, tetrahedral like we've mentioned once already, and 2 examples would be methane and the ammonium ion. Sticking with 4 regions of electron density, we also have the arrangement where you have 3 bonding pairs and 1 lone pair. That gives us 107 degrees, which is called trigonal planar, and a classic example would be ammonia. And still with 4 regions of electron density, the third arrangement is 2 bonding pairs and 2 lone pairs. This is called nonlinear and has a bond angle of 104.5, And the classic example we refer to at A level is water. And the final shape to remember is one called octahedral, which comes from 6 regions of electron density, all of them being bonding pairs but with no lone pairs. So octahedral has a bond angle of 90 degrees. The classic example we refer to as sulfur hexafluoride, or SF6. So this screen hits 2 simple ideas in one. First of all, some common molecular shapes and ions together. So we've got their names in blue. We've got their bond angles now added in red, and also their shapes now in purple. And just to clarify on the different strengths of repulsion, bond pair repulsion is the weakest, and the next strongest apart from that is bond pair lone pair repulsion, and then finally the strongest type of repulsion of all between electron pairs is lone pair repulsion. So sometimes in an exam question you'll not just be asked to decide what the molecular shape or the bond angle is, but also to justify your decision. You start by quoting the number of regions of electron density and then say that electron pairs repel as far apart as possible, but lone pairs more so than bond pairs like we've just looked at. Then you give the number of lone pairs and bond pairs present in the molecule. If you need to do a dot-cross diagram to reassure yourself of what this is, then please do so. Sometimes they'll give you a dot-cross diagram for this reason. If they do, in the question, make use of it. Then, assuming you've memorised the shapes we talked about a little bit earlier, decide what shape this represents and what bond angle this shape has, and write these down. And then finally justify your argument by saying that this shape is the shape of least repulsion, so this is the shape the molecule will adopt. Obviously not every single question requires all of this, so read the question, look at how many marks are on offer, and see how much depth or emphasis to use. All the points in blue above should cover you to a greater or lesser degree, dependent on what the question is asking. So let's look at our first example. They've given us a dot-cross diagram of hydrogen sulfide. I purposefully have not mentioned hydrogen sulfide in this clip, so I'm going to look at 3 examples that aren't in this clip to see if you can sort of follow along and apply the rulings and the ideas that we've looked at. It asks you to draw a diagram to show a likely shape and bond angle of a hydrogen sulfide molecule, and then explain why you've made that choice, and it's for 3 marks. So I've just made a couple of notes down to myself to help myself justify what I'm about to do. The sulfur is a central atom. It has 4 regions of electron density, and 2 of those are bond pairs, 2 of them are lone pairs, as you can see clearly from the dot-cross diagram. So from memory, because I've obviously made sure I've memorised these, I can say that it's nonlinear, that it's a bond angle of 104.5 degrees, and I can draw it out as a nonlinear shape with the 2 lone pairs at the top of my diagram. So I've stated that electron pairs repel, lone pairs more so than bond pairs. I've stated that there's 2 lone pairs and 2 bond pairs, hinting that that means 4 regions of electron density, so it's a nonlinear molecule and 104.5 degrees. So looking at the mark scheme, we got our 104 degrees, 104.5, sorry. They should have really put the lone pairs on there. This is a much older question from a previous specification, so in modern specification questions they'd expect you to put the lone pairs on there. There's 4 electron pairs, or 4 regions of electron density, and reference was made to electron pair repulsion in the answer as well. So this would obviously be a shorthand for the examiner's benefit of what they'd be expecting you to talk about. And it's quite interesting to say to see what it says about watching for bond angle between sulfur, hydrogen and lone pair. What they're talking about here is a bond angle between the lone pair and the bond pair. They're not interested in that. And the reason for that is it's not a bond angle. So a bond angle can only be between 2 bonds. not between a lone pair and a bond. So that's why they're saying that's incorrect. So this example asks you to draw a dot and cross diagram of a molecule of HOCl. It's a new molecule we haven't talked about in this clip, which is why I've chosen this question in particular. So the first thing I do is I draw my 3 atoms and I do my overlaps to show that this is where I'm going to put my my bonding pairs in. So I put one bonding pair between the hydrogen and the oxygen. And that's what I've come up with. You might notice that I've drawn the electrons in chlorine as slightly bigger dots, so you don't confuse them with the little dot, meaning the electron from hydrogen. So I've put a little key to make that clear. So I've first stated that electron pairs repel, and then I've augmented that. I've reinforced it by saying lone pairs repel more than bonding pairs, and electron pairs repel as far apart as possible. So in my explanation, I start by saying that electron pairs repel, lone pairs more so than bonding pairs. The shape adopted is based on that of least repulsion, and it's decided by the number of lone pairs and bond pairs around the central atom. So now we can move the page down a bit and look at the final part. So making the page a bit smaller so we can see just what we've written, because it tells us to refer to part B and CI. I draw up my molecule, not forgetting to put the lone pairs in on the oxygen. I don't need the lone pairs on the chlorine because they're not. The chlorine isn't the central atom, the oxygen is. So I put 104.5 degrees because it's obviously a nonlinear molecule. So looking at what we decided to put, electron pairs repel. The number of electron pairs surrounding the central atom decides the shape, and lone pairs repel more. So that gives us 3. We got the bond angle and we got the correct shape, and again I would recommend having the lone pairs around the central atom to support your decision. This one's slightly more applied in that you've actually got 2 bond angles within one molecule. But it needn't be challenging because you just need to think about the bond pairs and lone pairs around the central atoms. Notice I said atoms plural. So I've highlighted my central atoms in purple just so you can see what I'm talking about. And seeing that 3 of them happen to be oxygen, we know that oxygen will have 2 lone pairs. Because each oxygen has 4 regions of electron density, and the boron atom, as you can see, has 3 regions of electron density. So let's look at X first around the boron atom. So they only want us to describe why we think it's that bond angle. So I didn't worry about saying 3 regions of electron density. I didn't worry about calling it trigonal planar. I just went straight in and said 120 degrees. And my justification is 3 bond pairs and no lone pairs. But bearing in mind that it's 5 marks that we're after, you can see it on the bottom right of the screen, I said also electron pairs repel each other as far apart as possible. So that then justifies that the way they can get as far apart as possible is to adopt 120 degrees between them. So the bond angle Y will be 104.5 degrees because you may have spotted that it's very similar to water, analogous to water. And again we can list the bond pairs and the lone pairs here, but be careful of just saying electron pairs repel each other as far apart as possible a second time and expect to pick up a mark for it twice. They'll want something a bit more specific or sophisticated than that. And the key here is the fact that you've got 2 different types of electron pairs. So the new piece of information you'd need here to pick up your 5th mark would be lone pairs repel more than bond pairs. So looking through the mark scheme for that one, we got 120 degrees. We said there were 3 bond pairs for X. For Y we got 104.5. We said 2 lone pairs and 2 bonding pairs. We talked about electron pair repulsion, and we said that lone pairs repel more. So we got that last mark actually on several counts. Just a quick note, atoms don't repel. Sometimes people make the mistake of thinking it's the atoms that repel each other, because they mistakenly think that the electrons in the outer shell of the atom will repel the electrons in the outer shell of another atom. We don't think of it like that. That doesn't happen because the atoms are too far apart anyway. It's the bonding pairs and the lone pairs around the central atom only. So it's an important one to remember that. The reason that's in this particular mark scheme is because it's often something that examiners see, so they feel the need to put this in their guidance in their mark schemes. So let's do one more. So this next part's a bit combined. I'm going to do both parts of it because it shows you how shapes of molecule and other ideas come together in exam questions. So going back to empirical formula, using a periodic table, we put the percentage by mass divided by the atomic mass, or relative atomic mass, for each of the atoms concerned. And that gives us a very close approximation of 2 to 1 to 1 as our ratio. So that shows that phosgene is Cl2CO. So the next part of the question tells us that the molecular formula of phosgene is exactly the same as its empirical formula, so it's also Cl2CO. So it says, draw a possible structure including bond angles for a molecule of phosgene. So to help myself along, what I've done is I've done a dot cross diagram. Even though the question doesn't ask for a dot cross diagram, phosgene is a new molecule again. So to help me deduce what kind of shape it's got, if I do a dot cross diagram, I can see that I've got a double bond between carbon and oxygen, and 2 single bonds between carbon and chlorine. It's obviously going to be a 120-degree bond angle, and it's a trigonal planar shape. So I've drawn my possible structure, and I've included the bond angle. I didn't have to say it was trigonal planar, I just put that down for explanation purposes for this clip. Just like you didn't have to do a dot cross diagram, but I put that down for explanation purposes so you can see where I got my structure from. So let's now have a look at the answers to this one. So we got 2 to 1 to 1, and we did it by the correct calculations. We got our 120-degree bond angle, and we drew it in the correct shape. So that means it's drawn as trigonal planar. So hopefully it's been a fairly useful introduction or revision of shapes of molecules and ions. If you have any queries at this point, do jot them down and bring them into one of us at college. Have a chat to your teacher or maybe pop into a subject extension. But for now, thanks for your time and see you soon.